Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yes, good afternoon, everybody. So this afternoon, we have just heard 4 amazing, outstanding talks by amazing, outstanding speakers. So, and the theme of the event is interdisciplinarity, interdisciplinary research. So, without further ado, let me just invite all the speakers here on the stage. So, you know, giants of our field. I can't say it differently. So, please welcome Professor Kanade, Dr. Lampson, Professor Papadimitriou, and Professor Yao. So I have to say something while people walk on stage. So I was preparing for this panel, and I was thinking of a title, and then I was you know, thinking I'm very clever by thinking of this noun, interdisciplinarity, because when I typed this, so the word processor actually said that this noun does not exist. It's actually a typo, apparently. So interdisciplinary exists, but interdisciplinarity apparently didn't exist. Then I found myself very clever by actually making this a noun, by just, you know, making it anyway. And then just now I saw that Professor Yao's talk also uses this noun, so I feel that, you know, we co-create. So there is such a word. So it is, okay, good. So then word is wrong. Yeah, okay. So I have just prepared a few questions that should sort of start, let us go, and then in the end we can also open up for the audience to ask additional questions. So I'd like to start with a personal anecdote. About 10 years ago, I was meeting a very famous researcher, someone I admire very much. Maybe in the course of this discussion we will find out who this is. And so at that time, this person was doing research on sort of economics meets computer science, algorithmic game theory. And I was asking, you know, why did you start to think about this? And then his answer, of course, sort of somewhat tongue-in-cheek, was to say, well, you know, I'm a computer scientist. So I was thinking, how can I win a Nobel Prize? Then I was thinking, you know, economics, maybe biology, maybe physics, you know, economics is maybe the simplest one. So now, let's take this as a starting point, and let me ask, you know, moving forward, where do you think that, say, you know, computer scientists will be the first, where do you think that a computer scientist will win a Nobel Prize for the first time, and how long will it take?
I mean, didn't Herb Simon already win a Nobel Prize?
True. Yes.
That is true.
Yeah.
That is true.
The second one.
Second one. Yeah.
I have a conjecture.
Yes.
You know, in my biology and medical science, there are often Nobel Prizes given for methodology. For example, the inventor of the polymerase chain reaction has a Nobel Prize, got the Nobel Prize soon after, not very long after the discovery, actually. So I think that shotgun sequencing has changed the way genomics works in a comparably similar way. And I mean, I haven't done it, but maybe somebody should nominate Jean Myers.
Well, I think along that line, I think the Nobel Prize last year won for in chemistry, won by computer type of work, modeling the protein formation folding. I think that the person that it could have been a computer scientist, who does it, because I think that a computer scientist is perfectly possible to working together with the specialists to have that distinction. I think the main thing is that computer scientists don't seem to have the patience to work over 20, 25 years. Mm-hmm. Because I remember I met one of those persons in Stanford. At that time, I wanted to do protein folding. Mm-hmm. And so I went to see him and say that, is there anything interesting that one can do? And but I found out after talking to him and others, I got discouraged because it's more messy. It's not the kind of question that we typically solve that can be done in maybe a year or usually we don't do it
by Fox deadline. Yes, right.
So I think that for computer scientists to win a Nobel, I think that they have to be more dedicated to have more conviction about what they are doing, like the traditional disciplines.
No, but lots of Nobels have been won for fairly short-lived work. The PCR is an example, right. Or the double helix is an example. It doesn't have to be the output of 20 years of concentrated labor on one problem.
Well, I think it's more troublesome than the computer science could bear. If you think about the Watson, the two outsiders, they have to endure the jeering and the hostility of other people. They think that they are gadflies, and they have to think about the various tricky things they have to navigate.
So you think computer scientists have too thin skins?
I think we have two.
I don't think Christos' skin is particularly thin.
Okay. Really? Really? I don't know, but I think that.
You know, it's true that you have to, you know, to do that. You know, what Andy told us some very interesting principles about what is in the disciplinary work. What he didn't emphasize as much is the amazingly hard work that you have to do in order to penetrate sort of, you know, the way of thinking of a discipline that has been on its feet for centuries and running, and also the effort involved in convincing these people that you are worth their time.
Yes, I think Dr. Lamson had he had a lot of these quotes on his slides, and one of them was, I think, by Niels Bohr, saying that science is about, I can't quote it, but science is about sort of finding a notation to be able to talk to each other.
Finding a way to talk about the universe.
Yes, and so that sort of relates to this, right? So, I mean, obviously the question I asked was sort of, let's say, a more general one, in the sense that, let's if we think about Jeanette's talk about computational thinking, right? So we have seen today, throughout the day, we have seen many examples of how, say, computational thinking is influencing other sciences. Right? Many great success stories. You know, I mean, another question I'm sort of having is, you know, where's the limit of that? I mean, can we, you know, some time ago I was reading an article that said that for certain, let's say, low quality jobs, like, say, you know, the people work in McDonald's, for example, they want to basically create algorithms that the input to which is a CV, the output is higher or no higher. And apparently that's supposed to be more efficient than actually doing an interview. And so, you know, can this, or is this a computational way of thinking, can this penetrate even beyond, say, biology, physics, you know, chemistry? Can it go even, I don't know, can we ever win a Nobel Prize in literature? Or, you know?
Well, actually, this answer may be a little bit different. Well, in my mind, computer science is probably, or even engineering, is the only field which I think has separated physical manifestation or physical realization method with what is done, abstraction basically, or virtualization. And in that sense, actually, when it comes to Nobel Prize, it's disadvantage. Because if you say, okay, I got, say, my field, perfect intelligence machine. Now, when we say it, it may be the box, but we know what is inside is not important, is not a box, but what is being represented by that box. Whereas, in that sense, if AI perfect machine is realized, its impact is probably as big as blue LEDs. But blue LED is, here is the thing that you see. Okay? And then, so with that in mind, I don't think there's any limit, because as long as we have the world in which the physical thing is reality, has the problem to solve, then we have to represent it, we have to abstract it, and the essence of the solution is how the problem is represented. And I think that except a few things which you have to deal with the thing, there are enough of things. And I don't think, I'm not, at least for my life, probably, I'm not worried about things to do.
Yeah.
Well, let me put a more optimistic spin on it. I actually think that now that you asked this question, I actually think that that the time is on our side. I think that if you look at the Nobel Prize in recent years, say in physics or in chemistry, and it's quite often awarded not because of the deep theories, but its impact. So, for example, if you look at the Nobel Prize of Charles Kao, so for the fiber optics, and I think that the physics theory I mean it's not profound, but I think it's mostly because it's so relevant. It changed the world, and if you also look at other prizes, they are often about magnetic resonance and that have a very great impact in recent years, or new material which might have future applications, or the even quantum information processing. I think 3 years ago, the physics prize, one of the winners is David Winan for his work on a quantum information processing technology. It's the ion trap, and so I think that computer science has already transformed the world, and I think with all this new promise of machine learning, and I will not be surprised that we are going to produce some really fancy box, as you put it, has the intelligence in it, and I think they might just give the prize to a box. And its inventors, sorry.
In your mind, is there any say, field that computer science or computational thinking has not yet touched, that is waiting to be touched by us?
One field stands alone in my mind. It has been touched by computer scientists, it's brain science. Les Valiant has done some amazing work. There are a lot of people who are computer scientists and are doing brain science in the sense of imaging, data, and so on. I believe that it's a number. There is a bet. There is a probably less than 50-50 bet that there could be some very interesting theoretical ideas that will be needed to make progress. I mean, the problem is how does this bag of neurons create the mind? Okay, there is some chance that this needs some interesting mathematical insights.
But even short of creating the mind, there are much simpler things that collections of neurons can do. And we don't really understand how they do them in such a small number of cycles.
That's right. Yeah. So it's yeah. I mean, you read the standard graduate textbook in neuroscience, and in the sort of in the conclusion of the last chapter, it says you read it all. We know more and more and more, and still we have not even started thinking about what the overarching reality is. Yes.
I remember 40 or 50 years ago, Jerry Feldman tried to sell me on connectionism, and he didn't succeed, but he said something to me that has stuck with me for all that time, which is he said, we know what the cycle time of the nervous system is. It's a small number of milliseconds. And we also know that in half a second, humans and many other animals can perform a considerable number of fairly complex perceptual tasks. And we have no idea how to program a computer to perform those tasks in the 100 cycles that are available in the nervous system. Never mind whether it would make sense or be efficient or anything like that. We just don't know how to do it. So yes, I think there must be all kinds of opportunities in this intersection between neuroscience and computation. And my belief is that hardly any progress has been made so far.
So Takeo may have more information. It seems that that's a field that sort of, it's the field of the future every decade, okay? Sort of,
Yep. Go ahead.
Well, the interdisciplinarity, I mean, this is the discussion. Now, I don't know whether I'm a computer scientist, actually. Probably not. I've been working on the robotics from the beginning. And to me, working in that field, I have to work with on different disciplines from the very beginning. And one of the very somewhat cynical statement I tend to do is when I'm invited in computer science, so-called computer science conference as a keynote or something. I often shows the slides which says, I hate robotics is classified as one of the application areas of computer science. And in my mind, it's opposite. Robotics is one of the tools, or one of the application of robotics is indeed computer science to me. And then the way I say it is the world is physical. We are a physical being, and we can't live by eating bits. We eat physical things, we eat food and live in physical. So dealing with physical thing is indeed the core of almost everything in my mind. Now, as I said before, computer science did one of the greatest things, which is somewhat separate the physical realization with algorithm or whatever we call, and and then that's the reason why I think computer science is so dominant, and because we're not limited by the particular realization of the computing. Yeah. So anyway, because of that, I think from my point of view, things like physical science, physical things, physical reality, Internet of Things, and those things are natural things, and that's obvious. The direction that computer science has to deal with, more physical, more real world, and that's the source of the problems.
This is actually a great transition because you know, when there's an interdisciplinarity, there also has to be a non-interdisciplinarity somehow. And I was thinking, I think Professor Rosenblum or someone has in his speech today talked about the fear of becoming a mere sort of service discipline for others. And so I want to ask, you know, if say more and more, like a larger and larger fraction of computer science, let's say, is dealing with physical, or let's say is primarily dealing with physical part, is that primarily dealing with other sciences, to what extent should we have such a fear? You know, I was joking before, you know, I did my PhD in computer science. So I have a PhD in computer science. In 50 years from now, will anyone know what that is? Or people just study whatever, biology and other fields, and computer science just becomes a set of tools.
Well, we have a worked example that's several centuries old, which is mathematics. And Bell wrote a book 50 or 60 years ago, the title of which was Mathematics, Queen and Servant of Science.
Well, if we become the new mathematics, that's not too bad, so I don't complain.
Just what I'm thinking.
But will we?
Why not? If you believe Jeanette,
probably are, yes.
If you believe Jeanette, we certainly will.
I don't like to become a servant to other disciplines. I think that the answer to your question is not preordained. I think it depends a lot on what computer scientists, namely we, decide to do. I think that if we have this conception that let's not touch the other areas, and we'll just tell them what we know about computers and let them work out all the applications, then I think that will eventually become, I think it's worse than a servant. It's marginalized to a degree that essentially it will be, it's just like plane geometry. So my own preference is that we actively promote the creation of a greater computer science, in the sense that in computer science, I think that is sort of like the Carnegie Mellon School of Computer Science, that we would actively, we would expand the computer science department so that we have people who are actually working with a very heavy knowledge in other disciplines. And so we'll have our own computational biologists who are actually, could be biologists in training. And we have the physicists, we have the economists. So I think in this fashion, computer science will forever be an active participant and growing with all these other disciplines. I mean, it's not going to eliminate, I don't claim that we want to eliminate all the other disciplines. I'm just saying that let's have a method so that...
We need them, otherwise we'll be out of business. Yes, I mean, so right.
Yeah, so that would be my proposal. And one obstacle is that I don't know how this would be viewed in a typical university, because you are, I think, could be pushing it too hard. I think that that's why I actually thought in China there's a chance to realize this vision, because I think that exactly because the core disciplines are not already so strong that they have a very strong ego that it is possible to push for this. But I think that it's going to be very hard.
So I'm probably going to repeat what Andy said, except start from the end. I mean, I think that IAAS is an amazing example of computer science placing itself at the center, at the geometric center of the university. Okay, so where at the center, of course, of the scientific discourse. And I believe that this is what should happen everywhere. In some sense, mathematics is at the intellectual center of all universities because it has all these, because it has all these tentacles. Teaching, everybody must learn mathematics. In this sense, we are becoming the new queen and servant of science. Incidentally, when I think of servant, I think of an old film, an old amazing film that I recommend by Dirk Bogarde, where servant means somebody who radically transforms the master by dint of being powerful and necessary. Okay, so this kind of servant, I'll be proud to be. So, and I think in the United States what we are seeing is that a lot of kids, a lot of undergraduates want to study, want to study computer science. For example, in Berkeley, about 1/3 of the 6,000 undergraduates that we have every year take the introductory computer science course. And it's not because they have the ambition of becoming computer scientists, it's but because they think that this is what they should do. Jeanette mentioned that at Harvard, the most popular course these days is not the economics introduction, but the computer science introduction. So this is a sea change. I mean, it means that, even if we don't want to place ourselves at the center, the kids are placing us. The customers are placing us. But the point is that I totally agree with Thomas, that it is very precarious, very risky. It's not an easy task, okay? While being very imperialistic and ambitious, we should also take good care of our core, okay? Because that the core exists. It's there, our core values, our core concepts, our core abstractions. Okay? It's there, and it's expanding also. Okay, so so we should also, and the Simons Institute, which Andy was kind to mention, is very conscious that we have to offer our hand to other disciplines, but also with the same hand support the core discipline.
This reminds me of Professor Yao's diagram. Initially there were the two this Venn diagram that is moving together, where now the cores start to overlap, and I'm thinking of a third diagram, right, where basically the one core is sort of included in the other, or it just disappears, and then So let me turn this observation into a question. So I guess what is then the core? Let's say historically, simplifying a lot, of course, but say historically you could say that initially, the core of computer science to some extent was to try and make computers work, to be useful, increasing scale, efficiency, and so on, and developing the theory, the algorithms, and the theory necessary to understand and reason about these things. But moving forward, if say let's say more and more of the key attraction of computer science is to, like the interdisciplinary nature of it, then what of the core of computer science is still worthwhile really going deeper and really investing, 6 years of your life to do a PhD and expanding?
I think it will happen naturally because people are different. There are people who are really interested in some problems which have very little to do with other disciplines. And it's just that, for example, there are still people who work on complexity questions, saying that why is P not equal to NP,
Right,
and
right.
this is derivative.
Right.
I think we should leave room for that, and basically, I think that only by having a very large ability to do interdisciplinary work can we afford to nurture our core value, and because that's greater resource to justify what we're doing. And also, I think that one of the things that it's a little bit there's this phenomena that because in computer science we at least in theoretical computer science we tend to work on publish too many papers, and so as soon as we have done the easier problems, we cut off and we try to move on to new pastures. And now the hard problems we just left behind. And I think we have a lot of very exciting, interesting open problems on the stack. And let me just mention one that everybody can sympathize with, namely that at one point, say 30 years ago or 20 years ago, I thought that the theory of data structure is the thing for the future, is going to be as interesting and deep and as pretty as any mathematical field, namely that what's the best data structure for doing some problem. But it turns out to be so hard that I think that by now, very few people actually have the courage to attack such problems. It doesn't mean that you know, that I would love to see many of my favorite problems.
Bob Tarjan never gave up. You know,
Yeah. So I think that if we structure our field in a nice way, and so that people who work on core problems don't feel left out, if we have a reward system such that would let us keep our core, instead of having this fight, which a number of years ago there were the fundamentalists against the interdisciplinariness, and I think that's it was a stupid fight, and I think we can. I mean, there's enough room for everyone to do, and people should be recognized based on their contributions. I think it's just the same way that.
It's easy to say that it's a stupid fight once you have won it, right?
It seems to me that the core of computer science is dealing with complexity. There is an unlimited amount of complexity.
Complexity engineering, that's what we are, yes, exactly. Yeah.
And we're not going to run short of complexity to deal with anytime soon. And you can find it in a lot of different places.
Speaking about complexity, both Butler and Adi mentioned complexity. So let me, so there is, let's take the P versus NP problem, you know, which epitomizes complexity. I think that to do interdisciplinary work, first of all, you have to be recognized as a science, okay? And that's, you know, in other words, other sciences don't tell you go away, okay? Sort of, you know, you're not a discipline, okay? So when I started working in computer science, when all of us, you know, started working in computer science, this was not a given. Okay?
Absolutely.
You know, it was.
But it's not a big problem now.
Precisely. I mean, you know, so if we ask why is that, okay? There are three reasons that I can see. Okay. One is that they watched us solve amazing engineering problems. Okay. For you know, I'm speaking of designing databases, okay, sort of, you know, compilers, you know, so these are, there are a few amazing engineering successes, okay, that's one. Number two, and you can assign weights, is the P versus NP problem, okay? In other words, computer science is one of these disciplines from which pan-human, questions of pan-human interest can come out. Okay,
Yeah. And we have problems that are too hard for mathematicians.
For example, yeah, I mean, you know, that also will stay, you know, of course. I mean, if an amazing question comes up and then it's immediately squashed, yes, it's forgotten, right? But it will stay around. The third thing that put us, brought us to age, made us a giant among the other giant disciplines, was the internet. Okay, so you know that the internet, wherever it came from, has brought computer science to the people. In other words, now the whole world is our subject. Okay, so you know, and as a result, we cannot be ignored. Okay, so all these things, all right. I mean, you know, make us also realize that this is a scary situation. You know, it's precarious. What Thomas asked, will in 50 years people know what computer science was? And we have to look at the other two at the core, sort of, you know, the engineering core, or you know, the mathematical intellectual core, and that's where, you know, that's without a core we are nothing.
Right, but when I said complexity, I didn't just mean what
Absolutely.
people call computational complexity.
I could totally understand. I mean, you know, computer science is about taming complexity. So, you know, all of its aspects,
Okay.
all of the aspects of computer science. I totally got what you said.
I'm sure you did, but I wasn't sure that everyone in the audience did.
Why not including artificial intelligence?
Of course.
Absolutely.
It is indeed the topmost complexity of everything to me.
Absolutely.
Of course.
Supposedly, Marvin Minsky said many years ago when he was asked, what is going to happen with robots? Aren't they going to threaten all our jobs and so forth? Supposedly, he said, yes, robots will inherit the earth, but they will be our children. It's worth thinking it over.
But I think there's another an argument for that computer science will survive, but it's in a different sense. That I have gotten into contact with quantum physicists over the last few years, and so the quantum information theory actually it's a fairly integrated community, and I found out actually all these concepts that we cherish, including some of the very deep and recent work. I think the physicists have learned it. I think I think it's incredible that I believe that they have learned everything that the theoretical computer scientists have come up about quantum computation. And I think that they have learned all of it and they have exceeded us. And in addition, they have the added advantage in that they have a lot of things that they know that we do not know about, like many-body physics and so on. So I think that even if the theoretical computer science, at least the quantum branch, if it demises and disappears, it will live. Kind of is like in the I think what is this, the mitochondria?
Okay, of course.
So I think it's both. I think I'm happy for that because it means that other people also appreciate the concept that we come up with. It's also make me a little bit worried that what if every discipline, they really get their acts together. For example, the brain scientists or the biologists, they have found out that it's indispensable for them to deal with large database and they have to do deep learning and so on. And there are some really visionary biologists and so on. They say that let's just have a part of us that actually they have to study computer science and actually just combining with the biologist training and let's work on computational biologists from the biologist's point of view. And what if every discipline does this? I mean, the astrophysics, they deal with their simulation and they design the best data structure that the computer scientists have learned about. And I don't think it's totally out of the question. I think that it's certainly conceivable that it turns out to be advantageous. Instead of computer science would supply the intellectual capital to all the others. Every one of them just find, it turns out that it's better for them not to learn it from computer science. They have to develop their own. And so when I'm saying this, this is sort of independent, at least partially independent from what we do. That is, if you look at the physics of this, is it inevitable? I mean, it's just from the point of view of better research and so on, that we have to be this inventive. Is it conceivable? I would say it's possible. If I were a biologist or an evolutionary biologist, I would try to get my students to learn about what they're saying, that, well, there's a tremendous opportunity, and we as biologists, we are one step ahead of them because we know all the, this and that. So computer science, is computer science that, I'm not sure. I think the basic concept of computer science can be covered in just a few years, maybe 2 years, or at most 3 years. So, so I think there's a danger there. If I think about it seriously, I cannot sleep.
What was your last sentence in? If you think about your last sentence.
If I seriously think about it, I will not be able to fall asleep. About the demise, the dismemberment of the computer science. Well, that's just joking. I'm a staunch optimist.
I think I should change the topic in order to not cause insomnia with good. Okay, so we've discussed, let's say, bluntly, okay, so we've discussed what we can do to others, what we are ourselves. Let's ask what others can do to us, or what others have done to us. Okay, so I guess we briefly had a discussion before, and we said, okay, maybe computer science is somehow coming from math and physics and engineering. These are, say, the three, say, strongest influences that we have seen. Are there other, like, do you see other, let's say, methodologies or ways to approach problems or something that we see in other sciences that could actually be very, let's say, fruitful in computer science? We have heard about rhetoric today, so that's one.
I mean, it's a simple thing that Andy talked about economics. In the global information environment, in some sense, every system design is also economic system design. Butler had to talk about time to market, and so on. In other words, and every algorithm that runs must solicit its inputs from agents who would lie, and sometimes its gates are agents who lie. In the way that Andy described. So incentives is paramount. Okay, when we have systems that evolve from consent, that are not quite designed, then incentives are important. And economics is the science of scarcity and incentives. So that's one obvious answer I can.
Go ahead, Jeanette.
There's areas of computer science that require understanding human behavior. So psychology, cognitive science, social science, and also even human-computer interaction requires some sensitivity to design, which is not really a science, as I think all of us would consider. So there are even softer areas of human endeavor that I think influence computer science.
So I guess before...
One thing I learned from them is the meaning of users. I was doing quality of life technology to help people who need some, hopefully we can provide help for independently living. And computer scientists or roboticists, we tend to say, okay, users. And we say, oh, users want this and that. And when we began to talk with them, they don't like to talk users because, like, oh, the people who have visual, impairment, and then we tend to think, oh, this and that, and then we give certain small scenario or even not visually impaired people and put the mask and then see what we can do. And they say, no, that's not, you may be dealing with the users, but you're really doing with people. And that there's a big difference. And at least I learned how to do a little better job in dealing with so-called users. And that's one thing I thought I learned.
Right, there are only two industries that call their customers users. And unfortunately, we are one of them.
Better than the other one. I guess we can open up to the floor briefly, but I have one last question before we run out of time. So, to a new student who can decide to either study computer science and become interdisciplinary by also studying something else, or studying something else, studying physics, biology, and learning whatever he needs on the fly, what would you do? And secondly, what will a computer scientist do in 2030? In year 2030 or 2020 or 2010, or you can choose. Maybe a quick answer, and then we can have more questions from the floor.
So a quick answer for me is that the last 10 years, when I advise, I advise probably several dozen students at Berkeley, computer scientists. When they ask me, Professor, what else should I take? Should I take the second, the third theory course? And so I tell them, take linguistics, take business, learn economics, psychology. Okay, so in other words, I think that we should broaden a lot. We should encourage our students to because the world is our scientific subject now.
For many years, I've tried to, totally unsuccessfully, tried to persuade my academic colleagues that they should not admit into a PhD program in computer science anyone who has taken an undergraduate degree in computer science. Undergraduates should study classics or mathematics or physics or history or something with more weight to it than computing. Not that computing is bad, but it doesn't have enough. Another way of saying this is, I think you can get a very good undergraduate education majoring in computer science, but it's too easy, much too easy, to get an education that's much too narrow and doesn't have enough long-term value. And that's something that I think students really have to watch out for.
I partly agree with that. Robotics, often we say, computer scientists, pure, not as useful, we tend to say, because, sorry about this, but we say, oh, because they don't know what the world is moving around, physics. And we like people who, as Butler said, have some little bit different, more physics-oriented background, and then on top of it, have computational mind. Now, having said that, in computer science, I think producing interdisciplinary talent does not necessarily mean to me to teach other other disciplines within computer science. I think what we need is to people who have the mindset to work with other people. What does that mean? I think computer science is a very special field in the sense that if we minimize it to, say, programming, okay? Learn how to program itself is not useful because it has to be applied to some problem which may be changed from time to time. So in order to make it, you cannot be expert for everything, but the problem is the mindset of being able to talk to the particular field and then work with them. And so I think that's what it means, interdisciplinary education. That's a little bit different from pure, very deep research for which you have to be 50-50 or even 100 experts of computer science and the field. I think we have to a little bit separate undergraduate educational aspect of interdisciplinary and research aspect of interdisciplinary.
Yeah, my view is that I think we should be agnostic in terms of how to educate students. I think that we should offer all kinds of options. The student, if they want, they can be narrowly educated. And if they want, there is a possibility for them to acquire a very broad, even covering both humanity and science. I think that if we have a good structure so that the students can get advice from people who know them well. For example, if every student has an advisor in college so that they get to know better and try to give advice the best they can. I think that over the long run, people choose different options and it will become clear what would be the most expected outcome. And I think that we should just give infinite amount of freedom and see how it works out.
No, I think narrow and deep is fine. Narrow and shallow is not so good.
Well, but they're going to be...
That's what I worry about.
No, I don't worry about it. I think they are going to be punished in life.
Yes, but a lot of harm will be done first.
It's their choice.
Now we're back to evolution.
Yes.
Yeah, so I think we maybe have time for a few questions, like one or two, and then we move to the next. There's a question in the back.
I'm a roboticist. Most of my work is algorithmic. I have degrees in electrical engineering and applied math. But I teach in the mechanical engineering department. And when I hear the sentiment expressed throughout the day about the concern about can computer science survive or are we becoming a subservient discipline to other disciplines, I'm just amazed and my mind is boggled. Some of my mechanical engineering colleagues also worry when they work with doctors that maybe we're just becoming technicians to these medical types and we're not getting the proper credit that they deserve. So I think that concern is really misplaced. I wonder if the root of that concern is maybe has to do with education, specifically enrollment numbers. This is probably not the problem at Berkeley or CMU or Stanford, but many computer science undergraduate programs, from what I understand, the enrollments are declining. And in some sense that's expected because students, companies want not people who have operating systems expertise, but somebody who's computer savvy, can program and have domain knowledge. So I wonder if you can maybe address that point.
He's not asking that. He's asking programming system, operating system. Well, we know what to look at.
I don't think computer science enrollments are declining.
They're going up.
Right.
Where, you claim that computer science enrollments are declining at somewhere? In China they are?
Well, other parts of the world, for example, Korea, where I'm from.
because we also have the discipline of software engineering in China. So if you add them up together, maybe it's a different picture.
Okay, we have a last quick question, and then we have to move on. Yeah.
Hi, my name is Haochun Wang from National Tsinghua University in Taiwan. So there's another common way to divide a discipline for remote thinking people in terms of theoretical versus applied. So theory versus application. And that kind of distinction seems to have to say something about interdisciplinarity. So just want to hear about your perspective on this kind of divide.
I always thought that this contradistinction between theory and application is overemphasized in computer science. I mean, if you go to an electrical engineering department or a mathematics or a mechanical engineering department, and you ask where is the theory group, they will not know what we are talking about. Okay, they're engineers, and some of them work on whiteboards, and some of them work in labs. Okay, there is much more unity. I mean, and I think there is much more unity in the United States than we want to admit. Okay, in computer science than we want to admit. Having said that, so it's I believe that both people who whiteboard people and lab people can do very productive interdisciplinary work. And in different modes, of course, and in different capacities. In my, as I can see it, there are opportunities for both. I mean, the brain science example that I used, right now, only applied people are doing this kind of interdisciplinary work.
All right. So we're out of time, actually. So thank you very much to all the panelists. It's been really a pleasure and an honor. And thank you, everybody.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.